And this will be the lecture for Chapter 18. We'll be talking about thermodynamics, and the last lecture for Physics 101. What we'll kind of be talking about is we'll be talking about what thermodynamics is, and I'll talk a little bit more. I've already talked about a little bit about what it means when we reach absolute zero in the language of temperature, and how that's related to an internal energy of a system. We'll talk about the first law of thermodynamics, and we'll talk about a very special type of process called an adiabatic process and how that's related to meteorology. And we'll kind of wrap up with the second law of thermodynamics, which is a fancy word for entropy, which is saying that the natural order of things is, things tend to go from order to more disordered things. Now, when we talk about thermodynamics, what we're really going to be talking about is we're going to be talking about heat flow, we're going to be talking about internal energy, and we're also going to be talking about work and how all these guys are related. And it turns out that we really didn't know enough about this until about the 1800s. We just didn't know enough about the atoms or molecules or how all these things were put together. But really what we're trying to do is we're trying to link ideas of mechanical work, pressure, and temperature. Two things to kind of keep in mind that are really important to thermodynamics is energy is always going to be conserved, mechanical energy and thermal energy, and also the fact that when heat flows, it's always going to spontaneously flow from hot to cold. It's never going to flow in the other direction. Now we have talked about temperature quite a bit, and I've talked about how temperature is actually a measure of thermal energy. And it turns out that temperature is going to be related to the pressure of a gas as well as the volume that a gas will subtend. And it does so using what's called the ideal gas law. We're not going to introduce that formally here, but I do want to talk a little bit about how temperature is related to pressure and volume. And one thing to always kind of keep in mind is when we talk about the temperature in a physics class, we really want to use this Kelvin scale, which has an absolute zero, and this absolute zero, that's going to be the lowest possible temperature that we'll ever be able to reach. And when we talk about that in the language of thermal energy, when we hit absolute zero, when we hit 0 degrees Kelvin, we have taken away all of the energy that an atom or molecule may have. So we've totally stopped it from moving. Now, how is that related to pressure? Well, if you think about it, if we had something where we had a gas that was at 100 degrees Celsius versus one that was at maybe 200 degrees Celsius, then what's going to happen is well, temperature is related to internal energy, so it's kind of related to speed. So we've got some molecules in a box, and these guys are all moving at some speed that is dictated by their temperature, and they're all kind of bouncing off the wall here, and here, and that's kind of putting pressure on there. Probably not surprisingly, if we increase the temperature of this gas up to 200 degrees Celsius, then what's going to happen are these molecules are going to start to move faster. You can kind of imagine them bouncing off the box here, and here, and they're bouncing off faster. So as we increase the temperature, we're also increasing the pressure of a gas. And when we think about it in the language of 0 degrees Kelvin, well, if we take a molecule down to 0 degrees Kelvin, then it's not moving, and we would have zero pressure. Now, kind of similarly, as we change the temperature of a gas, the volume can also change. So if we had a gas right here sitting at 100 degrees Celsius, and we lowered the temperature to 0 degrees Celsius, it's going to take up less volume. These molecules are just not moving as much, so they're not pressing up against the piston by nearly as much. And it turns out that pretty much for every degree Celsius that we lower our temperature by, we're going to drop by 1 over 273 degrees Celsius. So you drop down to this one, you can kind of see we're taking away 100 over 273, we dropped 100 degrees. And when we hit negative 273, which is also going to be 0 degrees Kelvin, then the volume is going to work out to be zero, so the gas is taking up no temperature, and we'll never have a temperature below 0 degrees Kelvin, so we call it absolute zero. So temperature, this is the absolute lowest limit of temperature, and all the molecules have pretty much lost all of their kinetic energy. Kind of taking a look at it from maybe more of a solid sense, we're actually talking about internal energy, which is going to be the sum of kinetic and potential energy. So I kind of come back to my classic diagram of a solid where we say, this is a solid and the molecules are kind of wiggling back and forth, and how much internal energy they have is just going to be their kinetic energy, how fast they're moving at any given point, plus their potential energy, treating those chemical bonds as springs. One thing to kind of keep in mind is when we talk about thermodynamics, we're not going to be talking about the number that's associated with their internal energy, but more of how we're changing the internal energy of a substance. So how much does it change by? So let's kind of talk about how we can change the internal energy of a system. We can increase it either by adding heat into the system or putting some work into the system. If work is done by the system, then energy leaves the system. So this blob right here kind of represents what I would call my system, and it has internal energy that depends upon temperature. If we want that temperature to go up, then we can add some heat energy into the system. If we want that energy to go down, then that system can do some work. So that kind of leads us to what's called the first law of thermodynamics. It says if you want to increase the internal energy of the system, then you add some heat. If you want the internal energy to go down, then the system can do some work. I always kind of like to think of this as calories in versus calories out, and my body is going to be the system. If I go ahead and I eat a 1,000 calorie hamburger, and I don't do any work, then the internal energy, the fat storage of my system, is going to go up. If I go out and I do 500 calories worth of work, then okay, I'm going to maybe store a little bit of that as internal energy. If I went ahead and I did 1,000 joules worth of work, then my system kind of remains in equilibrium. Really, the first law of thermodynamics is just kind of saying energy is not going to go away. It's not going to go into the ether. It can't be created and it can't be destroyed. If we have energy going into the system and energy coming out, the internal energy of the system is simply going to be the difference between the two. So let's just kind of get a little bit of practice of this. Suppose we add 100 joules worth of energy into a system, then how much does the internal energy change by if, well, for part A, we're going to say 0 joules leaves the system. Kind of hope that you would say the internal energy of the system is going to increase. That's that positive sign by 100 joules, simply because we have 100 coming in when we have nothing coming out. Kind of ask the same question. If we have 100 joules of energy going in and 50 joules of work goes out, then what does the internal energy of the system change by? Well, we would expect it to go up, and we would expect it to go up by 50 joules. Kind of an interesting implication of the first law of thermodynamics is another way we can change or increase the internal energy of a system is we can do some work onto the system. So kind of think of heat is equal to internal energy minus work. So here I've kind of had my heat flow into the system, and before I had work kind of coming out. And now kind of the question that we're saying is, well, what if rather than the system does work, but what if I say, okay, I'm going to go ahead and I'm going to do work to the system? Well, you kind of see the arrow points inwards, and if the arrow points inwards, then energy is going into the system, and so the temperature can go up. So this is kind of like why when you rub your hands together, it makes them warmer. You're doing work, it's increasing the internal energy of your hands. And a fellow by the name of Joule had this funky little apparatus right here where it had these weights, and he allowed these weights to kind of fall down, and as they fall down they kind of turned this little paddle wheel, and what he was able to do is he was able to convert some of the mechanical energy that they had, some of their gravitational potential energy, into heat energy, which was warming up the water. Now, there's kind of one special type of process that I want to talk about. This process is going to be an adiabatic process. In adiabatic process, the heat into or out of the system is going to equal to 0. So we can kind of rewrite the first law of thermodynamics to say that the 0 is going to be equal to the internal energy minus the work that is done by a system. So kind of the drawing for this is we're going to have no heat flow out of the system. And if the system does work, then you would expect the temperature to go down. If work is done to the system, then you would expect the temperature to go up. So how do we get adiabatic processes and, again, no heat into or out of the system? We can do this by insulating the system really well, or kind of the more common one is performing the process so quickly that there's no time for the heat to leave. I have a nice little demonstration of a fire piston for you to look at, and that is an adiabatic process. So again, just to kind of sum up adiabatic processes, no heat is going to be added to the system, and so there's going to be an increase in the internal energy of the system if work is done on the system, and if work is done by the system, then that energy has to come from somewhere, and it's going to be a decrease in the internal energy of the system. So think of that fire piston, think about, when you use a bike pump, it tends to heat up. That's kind of what's going on. Okay, I want to give you a quick demonstration of adiabatic compression. I do have one of these, however it is currently broken right now. So it's called a fire syringe, and it's a good fire starter. And what you do is essentially, right in here, you put a piece of cotton, and then you compress it very quickly. Again, quickly means adiabatically, which means no heat can leave the system, and you can actually reach the flash point of paper or this little piece of cotton, just like you see right there. So now I just want to kind of change gears a little bit and talk about a system that can do some work, and that system is going to be the 4-stroke engine. Not surprisingly, there's 4 strokes. There's going to be the induction stroke, the compression stroke, the power stroke, and the exhaust stroke. And what I want you to really kind of pay attention to is where is the work done to the system and where is the work done by the system. So let's first start with the induction stroke, and here we kind of just have a little piston. It's got a little valve, or it's got a piston that moves up and down. And there's 2 valves on the top of most engines, and in the induction stroke, one valve opens up, and the piston works its way down, and it sucks some fuel and some air into the chamber. And kind of if we were to think about what is the pressure and temperature inside of this, the pressure is going to be roughly atmospheric, actually a little bit less because it's pulling downwards, and we'll call the temperature roughly ambient. The next stroke in the engine is going to be a compression stroke, and you can kind of see this valve right over here is closed. This one still remains closed, and right here the piston is moving upwards and is compressing it. Now we know that if we compress it, it's going to increase the pressure quite a bit. And we know that pressure and temperature go together, so as the pressure goes up, the temperature is also going up. So it's going to be high pressure and fairly hot. One thing to kind of keep in mind is, where is the work being done? In this case right over here, the engine is doing work because it's compressing the gas. I forgot to mention it, but it was also doing work on the previous slide. And now we have the power stroke, and actually I kind of broke that into 2 slides right here. In the power stroke, right here, the spark plug fires off a spark, and it ignites the gas, and that forces the piston down. So very high pressure, and temperature is very hot. And the power stroke is the only one where work is going to be done by the gas to the engine. Now, at the end of the power stroke, kind of the piston has worked its way all the way back down, and so it's a slightly less pressure and slightly lower temperature, right? The piston has kind of expanded just like that. And one thing I just want you to kind of remember is if you think about work and energy and all that good stuff, it really has to be worth it for us to burn gasoline, because all the other strokes of the engine except the power stroke, the engine has to do work. So we have to get more out of the engine than we put into it. So we get more bang for a buck in the power stroke than in all the other strokes put together. And then lastly we have the exhaust stroke, and you kind of see the valve over here has opened up. This one over here remains sealed, and the piston works its way back up through the chamber, so slightly above that atmospheric pressure, slightly above ambient temperature. But again, the piston is doing work to the gas in the exhaust stroke, and it's kind of setting it up for the next induction stroke. Now, you may be wondering, what does Octane have to do with this? I can go to the pump and I can buy the cheap stuff, or I can buy the expensive stuff, and chances are that if you drive a nice expensive car, then you're supposed to put the nice expensive gas in there. If you drive a cheap old beater like I do, then you can just get away with putting the cheap stuff in. And I've even putting in some 86 before, which is even cheaper than 87. Now, kind of the difference between these guys is gasoline is going to spontaneously ignite at a certain temperature, and as you compress the gas more and more and more, the temperature gets higher and higher and higher. So you can kind of see that 87 is going to ignite around 750, 90 is going to spontaneously ignite there, and 93 is even higher. Now, what happens if you go ahead and you put some of the cheap stuff into an expensive engine? Well, not surprisingly, those expensive engines have higher compression ratios, and so they tend to get higher temperatures inside of those pistons. So if you put in the cheap stuff, then it may actually spontaneously ignite before the spark plug ignites it, and that's going to actually cause knocking. So if you hear knocking or something like that, then you probably should be putting higher octane fuel in your vehicle. Kind of not surprisingly, the more efficient cars out here, like this one right over there, engine efficiency is related to how much they can compress the gases inside of them. Right over here, red General Hoopty might have a 10-to-1 compression ratio, and that's the ratio of the volume before and after compression. A fancier car might have 15-to-1, so higher compression, higher temperatures. Diesels actually have an even higher compression ratio, and they don't even use spark plugs, they use glow plugs. And kind of the fire piston that I showed you right earlier has a compression ratio of about 25-to-1. Not surprisingly, higher performance cars, higher efficiencies, higher compression ratios, they need higher octane.